Hi folks, we're going to start this lesson by taking a look at a problem that we had earlier on. Okay, so it was the problem of a 40-gram sample of a radioactive material that decays to 0.1 grams. And it turns out that we had to solve this equation to determine the time that it took for that to occur. Okay, and this is where we hit a wall because we have a variable in the exponent, and unfortunately we don't have any algebra to extricate that variable from the exponent. Okay, so this is our end goal for now, at least for the next couple of days, is can we figure out a way to uh, solve this type of equation? Okay, so the first step we took was to look at the inverses of exponential functions. Okay, so we took, as one of our examples, y equals 2 to the x. Okay, and we sketched the graph of the inverse function. Okay, and we determined a whole bunch of characteristics. So we were able to determine things like domain and range and behavior, asymptotes, intercepts by studying the original function y equals 2 to the x, interchanging the x and the y's, and figuring out what this inverse function should look like and how it should behave. Okay, but when we try to write an equation for this inverse function, okay, so again, y equals 2 to the x, and the way in which we determine the equation of an inverse function is just to interchange the x and the y. So we end up with x equals 2 to the y, okay, and we'd like to, in principle, be able to solve for y. But then we realize we hit the exact same wall as we had before when we were trying to solve that exponential equation. Okay, we don't yet have the algebra to do that. Okay, but the fact that we end up with the exact same scenario might tell us that inverse functions might have something to do with solving this type of problem. Okay, so this is where, again, we hit another wall. We do not have any algebra to solve. So again, let me take a more general example here. So y equals a to the x, where a is any valid base, so greater than 0, not equal to 1. And in order to find the inverse, I just interchange the x and the y. So x is equal to a to the y. Okay, so just a more general version of that example there. So again, we don't have the algebra to solve for y. And so essentially what we have to do is we have to make up notation to represent the inverse function of an exponential function. Okay, and what we have, and I again going to use this symbol here as meaning is equivalent to. So what we need is an equivalent way of writing this equation, which represents the inverse of a to the x, okay, but using notation that allows us to isolate y. Okay, and this is the idea of a logarithmic function. Okay, but when you think about it, the inverse of 2 to the x won't be the same as the inverse of 3 to the x or 1/2 to the x. So we need to indicate that this function is representing the inverse of an exponential function of base a, the same base as we're working with. Okay, so this equation here is equivalent to the one above. And what this function represents is the inverse. And as we talked about earlier, the inverse of an exponential function will be a function. So this is the inverse function of y equals a to the x. Okay, so there we go. We now have notation for the inverse function of any exponential function. The limitations are on a are the same. Since these are inverses of exponential functions, a has to be greater than 0, can't be equal to 1. Okay, but now we can treat these as their own functions. So for example, this function here, okay, can now be written as f at x equals log base 2 of x. Okay, and we have some okay, sorry about that. Just a big announcement, so I had to shut it off. Okay, so let's see where we were at. So here, this represents the inverse function of the the function a to the x. Okay. So I think we're talking about now here. We know that this can be represented with this notation. So we know that this is a function that passes through 1, 0, and as we saw earlier, passes through the point 2, 1. And so we can now work with this as its own function. Okay. But in trying to develop some algebra to work with these types of expressions, we're going to see that we're going to constantly be going back and using the exponential form in order to determine that algebra. Okay, the reason being is that we have a whole machinery to work with exponential functions. Okay, in particular, we have the exponent laws. Okay, so we're going to see that today we're going to start taking those exponent laws for exponential expressions and seeing if we can translate them into rules for operating with logarithmic expressions. So that's our work for today. Okay. But before I get there, I just want to bring up another property of inverse functions that's going to be very useful to us. Okay, so I just want us to recall about what this expression means. Okay, so what we have here is we have an input x, okay, which is being input into the function y. Into the function f. So let's say xy is on the function f. Okay, that means that yx is on the inverse of f. Okay, so let's see what this does. I put my input of x into the function f. It gives me an output of y. So now I'm taking the inverse function using this input y. But what does an input of y on the input function do? Takes me right back to x. Okay. So essentially, what an inverse function does, we can think of it as neutralizing the effect of the original function. So if I apply a function followed immediately by its inverse function, what I get back is just the original input. Okay. So this is a very important property of inverse functions. In particular, okay, if I have, say, the function 2 to the x, okay, and I want to then take the logarithm base 2 of 2 to the x, well, hey, I have the exact scenario that we have here. First, I'm applying a function f, and then to that output, I'm applying the inverse of the original function. So what should the result be? Just x. Why is this useful? Well, let's go back now. And here we'll come full circle. Let's go back to our original problem. Okay, we had 1/2 t over 15 equals 0.0025. So wait a minute. If I want to now get this exponent out of the exponent, in particular that variable out of the exponent, well, wait, I have a way now to neutralize that exponential expression 1/2 to this input. So I can take log base 1/2 of both sides of the equation. All right, but hey, look what we have here. We have the function 1/2 to the x followed immediately by its inverse function. So as we saw before, what is the effect of applying a function followed immediately by its inverse? To just give us the original input. So what is this whole thing equal to? Just that original input of t over 15. And so now we've achieved what we need to achieve, is a way to get a variable out of the exponent. There's one little problem now, because unfortunately we've hit another wall. If you look in your calculator, you're going to find a log button. What you won't find is a log base 1/2. Okay, so hopefully this algebra, this algebraic machinery that we're going to develop will help us to eventually figure out how can we use our calculator to evaluate that expression. Okay, that's it for now.